So my name is Justin. I'm an associate professor from the Department of Civil and Environmental Engineering in the National University of Singapore. So it's an honor to be here to address everybody with a small little project that we've been doing here in NUS. So some background of this project. This is a collaboration between NUS with Kajima. So for those of you who have not heard of Kajima, Kajima is a very big Japanese main contractor, and they have a huge presence in Asia and several other parts of the world. So we've been fairly lucky. We've been working with them over the last couple of years, and this little project was a kind of a thought experiment that we did with them to help them to improve their processes. So just some background about this little project. We have a lot of earthwork in Singapore, and when we do earthwork in Singapore, we have to do a lot of earth retaining structures, retaining walls, and so on and so forth. So one of the issues that we encountered with this was we wanted to see if we could challenge ourselves to come up with a robotic solution that could help us to automate the rebar installation in these vertical structures. Okay, so before I move on, I'll just give a shout out to my other team members, Mr. Hongjie. So he's a engineer in CATRIS, which is a Kajima Technical Research Institute in Singapore, and he's also a PhD student working with me. We also have Dr. Rongbo, who's a senior engineer in Kajima, Professor Quek Tong, who is in NUS Civil and Environmental Engineering, Dr. Chae, Soungho, also from Kajima. I think he's the Assistant General Manager, and of course myself. Okay, so I gave you some background. So this is a typical vertical structure that I was alluding to earlier, and so as you can imagine, trying to build such a structure, typically there's a lot of engineering constraints in terms of the structural integrity and durability. And vertical structures like these, they often lie on the critical path. So it's typically very labor intensive, despite all the heavy machinery that you would typically see on the construction site. And as you can imagine, it's a very physically demanding process. So in trying to do this, like I mentioned, this was a thought experiment. And when we sat down to design this process, we quickly realized that whatever initial designs of this system that we came up with would entail multiple arms or multiple robot arms involved in various different functions. And so we wanted to see if we could reduce the robot arms being employed on the site. So, one of the things that we wanted to do was to see if we could develop a practical on-site solution to place these long, loose rebars that you see on the vertical structures using only one arm to place them. Okay, so this is one of the early prototypes that we have in one of the Kajima labs that we've been working with them. So you can see this is what we're trying to do, where we are trying to place the rebar using only a single arm to control and to maintain the position of the rebar. Now, what you notice over here in this particular video is that the rebar bends very, very easily. And this is something that is going to impact the way that we're going to be placing if we're going to be only using one single arm instead of multiple arms. So there are a couple of scenarios in which this single arm rebar placement thing can carry on. One is that we could hold using a single arm, we could hold the rebar in the middle, or we could hold it at the end. But in whichever case it is, we're going to see a significant deflection, right, in the rebar when we hold that rebar up. So, when we started to dig into the literature, we quickly found that there were 4 competing methods. And we classified the 2 different methods. One was what we call the numerical method, which is based on physical principles. And for those of you who are inclined towards structural systems, you will find that we have identified the Euler-Bernoulli equation as one way in which we can predict that deflection. We also used a finite element method, which is based on some form of a large deflection assumption as the second numerical method. We also looked into data-driven models using a simple nonlinear regression model. And of course, then we also looked into neural network models to help us to predict the deflection. So we wanted to predict this. So what we did was that we carried out an experimental setup. My poor student had to run around the different construction sites collecting rebars of different lengths and sizes. He collected up to 27 of these rebars, diameters ranging from 10 millimeters to 32 millimeters. So these are standard sizes on the construction site. And the lengths of these rebars from 2.5 meters to 4 meters. And for each of these bars, we had different sets consisting of several different trials. So, to do that measurement, we set up a small, simple cantilever setup. We rigged a bench and then we placed that rebar on to mimic the effect of the arm. We use a simple clamp to grip the rebar, and then we measured the deflection using a laser sensor. So through all these hard work, we collected 154 data points comprising these 7 rebars of different lengths and sizes. So just to brush up on those, for those who have dealt with Euler-Bernoulli equations. So this is a physical equation, right, which is used to define cantilever boundary conditions, and it comprises different material properties such as the Young's modulus, the elastic modulus, the density, as well as G, which is the constant of gravity. Using these same material properties, we also created models with using the finite element method. So we created in NSYS, and we used very much the same parameters that we got from these rebars, and we put them in to estimate and predict the deflections. For the data-driven methods, we use a nonlinear equation based on what we felt was the most sensible from the physical constraints. And we did a nonlinear model, and we got these equations. Sorry, we got these coefficients following a series of fitting, right, of the nonlinear model. And finally, we also used a feed-forward multi-layer perceptron, a simple neural network with 2 hidden layers, and with 7 neurons within each layer, based on 2 inputs and just 1 output, which reflects the deflection. Again, the material properties that we used for most of all these models remained very much the same. Okay, so after we had done all these modeling, we put all the data and the results together. So what you see over here, I apologize for the small font sizes. We could have made them much bigger. So for each of the rebar size, what we did was that we did a simple comparison by superimposing the data that we created from the 4 different models. So what you can see over here, right? Just some quick observations from the results that we see here. One, of course, a lot of these are nonlinear behavior. We plot this against the actual data, of course. And right, as most of you would probably expect, the larger rebar diameters exhibit smaller deflections. This goes in line with physical properties. Longer rebars have greater deflections. Again, right, physics dictates this. And the larger and longer rebars, right, when we use the models to compare this, have greater variances in prediction using different methods. So what this basically means is that once you start having longer and larger rebars, that means that you have a higher level of uncertainty, and this is going to impact the kind of predictions you're going to be making. And of course, between all these models, we could quickly see also that the numerical methods, the Euler-Bernoulli and the FEM methods, they work well, but typically only for the shorter rebar predictions. And once you go beyond a certain length, the results start to get called into question. And so, having taken away those observations, we quickly went into looking into some of the quantitative analysis. So we put the different methods together, and we started to analyze and look and see whether we could see anything from the results. So let me just quickly introduce what we're doing over here. We use two metrics to measure the effectiveness of our analysis. One's the R-squared, and the other is the MAE, the mean absolute error. We also define two tolerances, right? So the plus minus 0.01 meters is a stricter criterion. So basically what this means is that we wanted to see for the data points that's involved, and if we give them an envelope of 0.01, how many of our predictions fall within this small little envelope? We also did a second one, which is 0.092, right? If you're wondering why 0.092, this was actually a value that was derived from the calibration when we used a camera, right, to try and see whether we could detect these kinds of variations. So to be honest, there is in the practical world, there isn't actually a kind of standard that defines how big a deflection is, right? There's no such tolerance. But speaking to several of the experts in Kojima and their subcontractors, they gave us a value of about 0.01 as being a tolerance in which they're comfortable with dealing with. So it kind of follows our 0.092 meter tolerance values. Okay, so that's the first table that we came up with. The second table, we mixed up all the different diameters and we started to look only at the lengths. So we classified the data that we obtained and we put them and we organized them according to the lengths of the rebars that we were estimating. So the outcomes that we see over here, okay, so you look at all those that's in bold, these means that these are the best results that we get from the tables. So the outcome is this. It's quite clear that the nonlinear regressions and the neural network models outperform the Euler-Bernoulli method. So it seems to say that the data-driven methods seem to provide better predictions. To be fair, when we compare just solely based on the diameter-based categories, right, which is in table 1, the nonlinear regression and the neural networks actually quite evenly matched in terms of the metrics. However, when we start to look at the length-based categories, which is in table 2, then we can see that the neural network model actually dominates the metrics for most of the different categories of lengths that we are provided. So what this actually tells us is that the neural network model seems to suggest that it performs better consistently, right? And if we were to focus on the stricter criterion of the 0.01 meters, neural network model seems to be more consistent throughout. Okay, so similarly, when we zoomed in further, we wanted to make sure that what we were observing in tables 1 and 2 was not a fluke. Again, we took the data and we started to repartition the data and run subsets of the data to see and make sure that we could get that we were observing the right things. So at the end of the day, again, the conclusions seem to hold. Our nonlinear regression and neural network models perform very similarly for the R-squared metric and the plus minus 0.092 meter threshold. And also the neural network model significantly outperformed the nonlinear regression model at the stricter plus minus 0.01 meter threshold. Okay, so so the data seems to suggest that, right, using a neural network model trained on the data that we have obtained seems to be able to give us some credible results. But there were certain irregularities. I think one of the if you notice in the table, one of the results was a little bit non-intuitive, and we started to look into reasons why that could be so. And we came up with two main reasons why that was. So the first is this, is that rebar shapes, right? The way that we have modeled, the way that we have assumed the rebars are that the rebars are a uniform circle. Unfortunately, right, the real world is not, that is not the case. The rebars are actually irregular in shape, right? They have ribs along the rebars, and then this will cause differences in the moment of inertia. The second thing also is that the orientation and the gripping of the rebar seems to suggest that there are some differences and might influence the deflection, right, when we grip the rebars in our experimental setup. Okay, so so with that, the results, right, seem to say that we have, right, that we are able to use a neural network model trained to help us to predict the deflection, right? And once we're able to do this, then this actually helps us in achieving, right, one small step in achieving our big dream of reducing the number of robots. So instead of having multiple arms of the robots to hold, we could now use a single arm and predict the next placement of that arm using the rebar deflection. So, so our work shows that the neural network model that we came up with seems to be quite promising. And like I said, this is a small first step to helping us to realize efficient motion planning for single-arm robot rebar placements in the future. Okay, so thank you so much.